Okay, welcome. So, we're been learning about thermal energy. And one of the things that happens when you heat things is not everything heats at the same rate. And this should be kind of common sense. If you think about putting two things on the stove, let's say you have a pan of water and then you have a equal sized pan of maybe beans. You turn the burners on and they're the same. One of them is going to heat up faster than the other one. Particularly metals heat up very quickly. So this chart right here has the specific heat of some different substances. And so let's take a look at this. Different substances take different amounts of thermal energy to change temperature, which is why they would heat more quickly or slowly than other things. For example, if we had a kilogram of aluminum and a kilogram of water and you put them both on the stove, which would change temperature the fastest? We said the aluminum, you would be correct. This is because water has a higher specific heat than aluminum. The water would heat much slower as it takes more energy to change temperature. The specific heat of an object is the amount of energy it takes to raise 1 kilogram of the substance 1 degree Celsius or Kelvin. Below is a table that shows the specific heat of common substances. Notice that water has a very high specific heat. High specific heat of water means the ocean can absorb a great deal of thermal energy without a large change in temperature. And this is what allows the oceans to regulate the temperature of the Earth. So you can think like when you're at the beach and you come out in the morning, the sand and the water are at about the same temperature. As the sun shines down on the sand and the water, it's the same sun, but the sand changes temperature much more quickly. And it gets really, really hot by the middle of the day and the water is still cold. One of the reasons is that sand has a much lower specific heat than water, so it takes less energy for its temperature to change. Silver heats very quickly, so it doesn't take very much energy at all for a kilogram of silver to be raised 1 degree. Water, on the other hand, has a very high specific heat. It takes a lot of energy to change the water's temperature. So water, absorbs a lot of energy. So that's why the oceans can absorb so much energy from the sun and they don't change very much. There is an equation that's used to calculate the amount of energy that's changed substances. And the change in energy, or the total thermal energy, is equal to the mass of the object times the specific heat of the object, which would be in a table like this, times the change in temperature. And the change in temperature is the independent variable. It's what you control. And what depends on that is the amount of thermal energy. Delta means change in. So as you go higher in math, a lot of times you'll see variables like this, and it'll say delta T. This just means the change in temperature. To calculate the change in anything, remember, it's always the ending minus the beginning. So like when we did change in speed, it was ending speed minus beginning speed. So delta T is the ending temperature minus the beginning temperature. Okay, so let's look at how we would apply this. So here's our equation, Q equals M times C times delta T. Q is the change in energy, M is the mass of the substance, C is the specific heat of whatever they tell us the stuff is, and then delta T is the change in temperature. So how much energy would it take to raise 1 kilogram of water 15 degrees Celsius or Kelvin? Well, here's our formula, Q equals M times C times delta T. Q is what we're trying to find out. It tells us right here, M is equal to 1 kilogram. C, it's water. The specific heat of water is in the table, 4,180. And the delta T, it says it's going to change 15 degrees. So now we can plug all this stuff in the equation and multiply it together. So we have mass is 1 kilogram times the 4,180 joules per 1 degree Kelvin times the 15 degrees that it's going to change. So the thermal energy to change that 1 kilogram of water 15 degrees is 62,700 joules. Let's suppose instead of 1 kilogram, we had 100 kilograms, and we wanted to change temperature the same amount. Okay, so here's a little formula. Q is still what we're trying to find out. The new mass is 100 kilograms. The specific heat of water is still 4,180. And delta T is 15 degrees. So they're both going to change temperature the the same amount. So if we had two samples of water and they were both at 50 degrees, and we heated them by 15 degrees, they'd both end up at 65 degrees. So we can substitute now, mass is 100 times the same specific heat of water times the same 15 degrees. Now it's 6,270,000 joules of energy to change the water. Notice we have 100 times as much water and it takes 100 times as much energy. So one of the things we put in the notes was we said that temperature is the average energy. Both of these samples of water have the same temperature. If they started at 50, they both ended up at 65 degrees. But the larger amount of water has a lot more thermal energy in it. Okay, we added 100 times as much thermal energy to it to raise its temperature to the same temperature. Okay, so notice how the mass affects the thermal energy. The only difference in these two examples is the mass of the water being heated. Okay, other numbers are the same. Okay, now let's think of a different problem. Scientists have learned that the temperature of the ocean has increased 1 degree Kelvin because of climate change. Is this a big deal? Like the ocean is still cold. And when I first heard that, I was like, so what? One year when I was teaching, the kids asked me, like, well, what does that mean? I don't know, it doesn't sound like much, but we were doing this, we decided, well, let's figure it out. So what's the energy needed to raise 1 degree Celsius or Kelvin? Well, to figure this out, we need to know the three variables in the equation. M is the mass of the water in the ocean. We already know what C is. The specific heat of water is 4,180 joules per kilograms of water, and the change in temperature is 1 degree. So I looked it up and found out there's 1.4 times 10 to the 21st kilograms of water in the ocean. It's a lot of kilograms. Okay, so we have our equation, and here's what we know. Q is what we're trying to find out, the energy to raise the temperature of the ocean 1 degree. The mass of the water in the ocean is 1.4 times 10 to the 21st. C is 4,180, and the change in the temperature is 1 degree. So now we can substitute the variables into the equation, the M, the C, and the T. We just multiply them together. When we do that, you get energy to raise the temperature of the ocean is 5.852 times 10 to the 24th joules. So that year the kids are like, well, what does that mean? I'm like, I don't know. It sounds like a lot. So we said, well, why don't we use something that we know released a lot of thermal energy? So the bomb over Hiroshima, the atomic bomb, well, that released a lot of thermal energy, and you can kind of imagine that. We saw how it devastated a city. Well, that atomic bomb released about 1.5 times 10 to the 13th joules of thermal energy. So if we take the amount of energy it needed to raise the ocean by 1 degree, 5.852 times 10 to the 24th, divided by the thermal energy in the atomic bomb, it would take 3.9 times 10 to the 11th Hiroshima bombs of energy to raise the temperature of the ocean at 1 degree. 3.9 times 10 to the 11th is 390 billion Hiroshima atomic bombs to raise the temperature of the ocean 1 degree Kelvin. So is it a big deal that the temperature of the ocean is raised by 1 degree? The climatologists are, thinking about that. They're thinking about this amount of energy has been added to the water in the ocean, and this is what drives the storms in the atmosphere. So when they say like storms are going to be more severe in the future, they're thinking, well, yeah, there's 390 billion atomic bombs worth of energy in the ocean that are going to be released into hurricanes and different weather events. So yeah, it's going to be a lot more serious. That's all there is for right now, and we'll see you next time.